For the rest of our day, we're going to get into 8.2. The only thing I want to talk about is something called function notation. That's one of those words you have to say very carefully when you're on videotape. That and shift. We're going to be shifting graphs in section. We're going to do lots of shift. That's some serious shift we got going on. Okay. That joke never gets old. Function notation. And we'll talk about some graphs of nonlinear functions, but we'll do that next week when we come back. Function notation, we've seen it in this class before, but I've never explicitly gone over it, and I want to do that today. This right here, when you see f of x, that's how you say that, when you see f of x, that's called function notation. And what this is this stands for a function, bless you.
Thank you.
Stands for a function whose what we call independent variable. Whose independent variable, that's a variable you plug stuff into. Independent variable is what you plug stuff into. Whose independent variable is what? What's the variable up here? It's x, yeah. That's all this is saying. It's a function whose independent variable is x. So it tells you the name of the function, that's f. It tells you the variable of the function, that's x. And the reason why we use this is, I've talked about this before also. We could write the same function two different ways. This is how we normally see functions, right? We've been dealing with this a lot. Y equals 3x plus 2, or f of x equals 3x plus 2. These two things right here are exactly the same. If you graph this one and you graph this one on a graph, you would get the same looking line. If you follow me on that. Same thing. Why in the world do we even talk about this when we already have this one? And the answer is for two reasons. The first reason is, if you need to graph more than one line on the same set of axes, this way lets you identify them. This way doesn't, because all of these will be y equals, y equals, y equals. You can't tell the difference just by looking at the line, right? This one you do f of x, g of x, h of x, and so on, and identify every unique line. You with me on that? Also, what's kind of nice is if I tell you, let's plug 2 in. If I plug in 2, how much am I going to get?
8.
Yeah. So if I plugged in 2, I'd say y would equal 8. Right? Does that tell you what I plug in just by looking at this? And the answer is no. If I plug in 2 over here, here's what we could do. We'd say f of 2 equal 8. That not only tells you what you plugged in, it also told you what you got out. Does that make sense to you? So here, if you plug in 2, I just told you that, and you know it, but it doesn't say that here. So if someone else were reading this, they'd have to do the work backwards to figure out what you plugged in. Here, I say, oh, what did you plug in? What did you plug in?
2.
Yeah, look how it took the place of x. You plugged 2 in for x, right? And what did you get out of it?
8.
This gives you an ordered pair. This gives you a point. Anytime you see this function notation, you can say, oh, I plugged in 2, I got out 8. That's kind of nice. It makes things a little bit easier for someone else who didn't do the problem to recognize your points. And that's one of the reasons why we use that. Well, I think that's about it. Do you guys understand the idea of function notation and why we're going to use it? Okay. Okay, so let's start talking, like I said, about square roots. Finding a square root is literally just the opposite of squaring a number. So while squaring a number says take a number, multiply it by itself, what do you get? Square root is the opposite. It says take your number, what number times itself will give you that number. So we're going in reverse of squaring a number. With that in mind, and I know you've all seen square roots before, so these should not be a surprise to you. That's the square root symbol. This is the square root of 49. So what is the square root of 49? The question is, what number times itself will give you 49? How much?
7.
Good. Now, is it 7 or the square root of 7?
7.
It's just 7. You don't keep writing that square root. So once you take the square root, you're done. So what I mean by that is, here it's pretty clear we have 7, right? But if I give you something like this, what I don't want to see is, oh, the square root of 16 is,
4.
and the square root of 4 is, we don't do that. Okay? Once you take the square root once, you're done. I mean, it's just one little step. Does that make sense to you? You don't keep taking a square root until you can't possibly take it anymore. That would kind of ruin your problems. So with this one, we're not talking about the square root of 4. We're talking that the square root of 16 really is just, well, it's just 4. Let's try a few more square roots. That'll pretty much be about it. How about the square root of 121? Anyone know the square root of 121? Good. How about the square root of 36? Good. Well, you guys are really good at this. It's fantastic. How about the square root of 1/9? Is that okay to take the square root of a fraction?
Yep, 1/3.
Why?
Because if you put the second power on both of them, it makes 1/9. Like if you get 1/3 and put squared on both, it makes 1/9.
Like that and like this?
No, without the.
Okay, well, you can do this. This is legal. And that you are right. You are going to get the square root of 1 is how much?
1.
And the square root of 9 is 3. So that's how we do get the 1/3. We take the square root of both the numerator and the denominator. That works out for us. We're going to learn later that a square root actually is an exponent. Not an exponent like 2 or 3 or a whole number like we thought, but something else. It's kind of interesting. How about the square root of 1 over 81? How much is that? 9?
1 over 9.
Oh, 1/9. Good. How about the square root of negative 64?
8.
Okay.
Negative 8.
Negative 8?
No.
Positive
Why? I don't know. You guys are guessing now, huh? Let's say we did 8. What's 8 times 8?
It's not, you can't, there's no square root.
Explain that.
You can't multiply 2 negatives. Well, you can't do a positive. It's not the same. You know what I'm saying?
No, you're just getting mad at me. Don't get mad at me. Yeah, you're right. You're right. You actually explained it really well. You can't take a negative times a negative and get a negative, can you? You can't take a positive times a positive and get a negative, can you? Only way you can do that is if you take a positive times a negative. However, that's not by definition the same number, is it? So you can't do this one. You go, okay, if I picked 8, 8 squared is 64, negative 8 squared is 64, not negative 64. So in this example, you go, how am I supposed to take the square root of a negative number? And you can't do it in what are called the real number systems, like integers, rationals, reals. You can't do it. It's not possible. Now, when we get further on in this course, we will be able to accomplish this problem, but it won't be in what are known as real numbers. Remember talking about real numbers as far as domain goes? It's pretty much every number that you know of right now. You're going to learn a different number system in a few weeks, like 3 weeks. We'll talk about that. It doesn't make it any harder or anything, but it says that this is possible there. For right now, what we're going to say is there is no real solution. Don't put no solution, because we will find one eventually. It's no real solution. Now my question is this example different than this example?
Yes.
What do you think?
Does it become negative after you find out the square root?
That's what it does. This is saying the square root of negative 64 where the negative is inside that square root. This one basically says this. How much is the square root of 64?
8.
Now take the opposite of that. So this is the opposite or the negative of the square root of 64. This one has a solution. This is just fine. This is negative 8. Notice the difference? If the negative is inside of our square root, yeah, we can't do it. That's no real solution. But if it's outside, it's really not being applied to that square root. Okay. Again, which one's possible here? The top one or the bottom one?
Top one.
Okay, top one will be how much, folks?
Negative 12.
Good. And the bottom one, again, we say no real solution. No real solution. Would you raise your hand and feel okay talking about these square roots? Good. So we can take square roots. We know that if negatives are outside the square root, that's okay. But if they're inside the square root, that's not okay. That's no real solution. And finally, when we take a square root, we don't keep writing the square root. Once you do it, it's over. You're just done. You do it one time and then you call it good. With me on this? Okay, very good. Now, let's talk through the rest of our time in section 8.2 about some nonlinear functions. Quick question for you. What did linear mean, by the way? Okay, if linear means line, what's 9? It means 9 lines. I am part German. You know that, right? I could say 9. Like Arnold Schwarzenegger. I crushed this mathematics. What now?
The cheating man.
The run instead of the running man?
No, cheating man.
Yeah, okay. Did he cheat? I don't watch the news.
He has like a 10-year-old kid with the nanny.
Yeah, but if you're rich, it's okay.
I would just shut up and smile.
It's called a double standard. You guys didn't know those exist? Anyway, if it's not just politicians, it's rich people. Happens all the time. Like me, I'm super rich, right? I can do whatever I want. So that's awesome. I'm famous, obviously. So if linear means line, what does non-linear mean?
Non-line.
Non-line. That doesn't mean we're going to be drawing dots everywhere. I mean, lines mean for us straight lines, so we're going to be drawing curvy lines somehow, or non-perfectly straight lines. Are you with me on this? That's what we're going to get out of these things. However, we really don't know the shapes of any of them at this point in our studies, so we're going to have to make some tables up like we did before. So in order to do your nonlinear graphs, like on your homework, what we're going to do is make up a t-table, and there's one key point here. So make a table. The thing about nonlinear graphs is they're not lines, so you don't know exactly what they're going to do on each side of the y-axis. For that reason, we have to pick some positive and some negative numbers. Does that make sense to you? Because sometimes they switch at the y-axis. So make a table, but use both positive and negative numbers. Let's do a couple examples here. By the way, when your book talks about function notation, all it means is it's using f of x instead of y. That's the only thing it means. So function notation would be like this. Let's graph f of x equals x squared. That'd be kind of nice, right? We've dealt with a lot of x squareds in this class. We'll finally be able to see what these things actually look like when you graph them. And I also want to talk about g of x equals, let's try negative x squared. Well, x there and g of x. X's again are what you put in, the g of x's in this case are what you get out. And here we'll have x's, and not g of x's in this case, but f of x's. Also, because these aren't straight, you need more than 2 points to graph it. You need more than 3 points to graph it. We're going to choose 5 points to graph it, okay? Because we don't really know these shapes anymore, or at all, really. Once we get the shapes down, we kind of understand what these graphs look like. We're not even going to have to use a table. We're going to be able to shift things around. That'll be in the next section, or 2 sections from now. But for right now, we're going to have to graph these with tables. It means we have to draw lots of points. Are you with me on this? So, we need positives, we need negatives, and we need 5 of them. What point are we for sure going to include in every one of these graphs, do you think?
0.
For sure, absolutely. So I'll definitely have a 0, but I want 2 to the right of 0 and 2 to the left of 0. So 2 positives and 2 negatives. Doesn't really matter which ones you choose, pick something easy. So I'll pick like 1 and 2, and -1, -2. Over here, I'm going to pick the same exact points. Let's see what we get when we plug these in. Just like we did with other tables, we'd have to take our x values, plug it into our function, and then see what we get out of that. So, with 2, we're going to plug 2 in. How much are we going to get out of that thing? Good, because 2 squared is 4. Okay. And we get ourselves a point, 2, 4. Are you all seeing where the 2 and the 4 come from? The 2 I made up, the 4, we get that from plugging that in. Raise your hand if you're okay on that 4. Yes. Okay, we're squaring things. So what this says is, if you want to see the extra step, we'll do it one time. This says how we're getting this is we're taking the 2, we're plugging it in, we're taking 2 squared, that's giving us 4. We have 2, 4. Okay, next one, we plug in 1, how much do we get out of that, ladies and gentlemen?
1.
Good, so we have 1, 1. We plug in 0, what do we get out of that?
0.
Nice. 0 squared is still 0. How about this one? -1, -1 squared. How much is -1 squared going to be?
1.
Good. Here's how this looks. I want you to pay close attention because this is going to be slightly different on the right-hand side. When you plug in -1 to this expression where it says x squared, what it says is you're taking -1 in parentheses squared. You with me on that? It's taking all of -1 and squaring it. -1 times -1 gives you +1. So our point is -1, +1. Yes, no? Okay. Next one, very similar. -2 squared, you're going to get how much?
4.
+4?
Oh, yeah.
+4. Because you're going to take -2 times itself. That's a negative times a negative, it's a positive. You get -2, 4. Not sure if you're alright with that. See where those numbers come from. Let's graph it and see what this thing does. In order to graph your line after, this is the hard part. This is really the hard part, actually plugging things in. Once you do this, it's just plotting points and then seeing what the shape is. First point that we did was 2, 4. I hope you all remember how to plot some points. 2, 4 means you go over 2, you go up 4, and that's where you put your point, right there. Next one we graphed was 1, 1. Well, that's not too bad. 0, 0, well that's just our origin. We'll put that down. Now the other ones, -1, 1. How do you get to -1, 1? Okay, so that should be, wow, this is weird, because right now it looks almost like a straight line. In fact, this isn't even a straight line yet. But if you were to just graph the side, this is why I said you have to have both sides. Look at the board right now, please. If you have just this side, doesn't it look like it might do that? It looks like it might do that. But once we graph the next point, if you didn't have your negatives, you would not see this next part. Once you graph your next point, well, that's -1, 1. That's up here. Wait a second, that's not what we expected, right? Just by looking at the right-hand side, that doesn't look like that should happen. Next one is -2, 4. That's -2 up 4. That's like right here. So what in the world is this graph doing? Pass it this way. There you go. There you go. It's all good. Just roll sheet today, guys. I don't know what's going on today. Did the video in the morning, or did the power screen in the morning, and screwed everyone up, didn't I? All right. Still gets passed the same way. So we graph both sides of y because we have positives and we have negatives. We want to see what happens on both sides. It changes right here. I mean, it's not going to be expected in some cases. Now, how in the world do you graph the rest of this? What do you do next? I don't want you to use straight lines. These are not straight lines. It's not like you should do this thing and go, oh, this is straight line, straight line, straight line, straight. It's not going to be like a weird looking V. This is a nice curve. The shape of this graph is, if you've heard it before, it's called a parabola. It's a parabolic curve. It means it's real smooth, makes like a U, or a U this way. So in our case, here's what you do. Start at the origin, or wherever your vertex is. The vertex will be the lowest or the highest point of your parabola. So right here, that's our vertex. Start there and make a nice smooth curve connecting the dots. Make it symmetrical on the other side. And that's about what we should get. Now, that's not the best looking parabola I've ever drawn, but hopefully you have the idea that it's a nice smooth curve. Do you guys get that idea? Now, why does it climb so high? Look at that. If I plug in 3, how much am I going to get? 9. Okay, you're with me on the idea, right? If I plug in 4, I get 16. If I plug in 5, I get 25. If I plug in 6, I get 36. 8, I'm already up to 64. It's going to climb very highly. It's climbing really, really fast. So every number we take, we square that, it's going to go pretty quick, isn't it? How many people feel all right with this graph? Name of it is parabola. Say parabola for me.
Parabola.
Good, all right. Now, what's going to happen when we do this? This right here, this idea of putting a negative in front of our function, what this does to this graph is going to stick with it every time you see a negative in front of your function. This is part of our shifting, and this is going to go in our next section. We're going to take this and run with it. But we want to find out what happens here first. So, when I take g of x equals negative x squared and we plug in 2, here's how this looks. It says you're taking negative. Notice how the negative is not within parentheses. I need you to notice this, folks. That negative part of it, this one, is actually not being squared. This says negative 2 squared, like that. In your pre-algebra class, you were taught that if you don't have parentheses around the negative, this is very, I'll show you this one time, hopefully it sticks with you. This right here, negative 2 squared, is different than negative 2 squared. Do you believe me? You should, because I know what I'm talking about. But this is actually true. This is negative 2 times negative 2. That's 4. This one says this is negative 2 times 2. This is negative 4. How you can think of it if you really want to is order of operations. What do you do first, multiplication or exponents? This really is negative 1 times 2 squared. You could do that. You could do that here. You can't do that here. You could do that here and say, oh, exponent says 4, and then multiply by negative 1 if you want to. That's negative 4.
Would it help to put parentheses around the 2 to square? That way you
Like-
don't forget that
Like
it's
this
separate.
one?
Yeah.
You can if you'd like.
I mean over both. So you remember to do the exponents first and then multiply it by negative.
If you want to, you can do that. Or just remember that if there's no parentheses, the negative is not with that number when you're taking it to the exponent. You can remember that way too. That's the way I like to do it. Exponent with parentheses, yes, negative goes with it. Without parentheses, no, it's not going to go with it. Does that make sense to you? So that's our idea. So in our case up here, this is not going to be positive 4 again. This one is different than this one. These are two different things. That'll be negative 4. What's the next one going to be then, do you think? So this is negative 1 squared, or negative 1. 0, that's a nice one. I'll take care of that one for you guys, so I don't want to waste your brain power here. If I do 0 squared, I'm going to be getting out 0. A couple other interesting ones. Let's see what this says. Watch carefully. Watch carefully. What negative 1 says is, I have a negative. That negative is this negative. You with me? Then I have x is negative 1. That one is in parentheses. That was my x value in this case. How much is negative 1 squared?
Negative 1.
Negative 1, very good. Because the negative 1 squared, this one, gives you positive 1, then you make it negative. Does that make sense? So this is negative 1. Lastly, we have a very similar situation. We'll have negative 2, negative 2 squared, negative from here, negative 2 being squared, and that's -4. So our points, I'll write them over here. We have 2, -4. We have 1, -1, 0, 0, -1, -1, -2, -4. Why don't you plot the points yourself? See what this thing does. So we've already done the hard part of actually finding the points. Now plot them on your graph, it's just finding the right coordinates. So 2, -4 means write 2, down 4, put a point. 1, -1 means write 1, down 1. 0, 0, we're at our origin. -1, -1, hopefully you got this. -1, -1's right here. -2, -4, that's down here. How many people got those points like that on their graph? Good. Does it look similar to the one we just did?
Yeah, it's just coming down.
Yeah, I'll tell you something. Every time you have an x squared, every time you have a square, and that's your largest power, your graph is going to be a parabola. Not sure if you're okay with that. Every time you get x squared. So all those things that we factored with the diamond problem, remember the diamond problem? Every one of those problems will be a parabola. Every one of them, when we graph them, is going to be a parabola. Isn't that kind of interesting? Every time. Whether it had the x and a back end of that or not. Every single one of those is going to be a parabola. Now what's the difference between... Draw those arrows, it keeps going. What's the difference between this one that we drew with x squared and this one we drew with the -x squared? What was the only difference that happened here?
The direction?
Yeah, was it a different shape?
No.
Same shape. In fact, if I took this one and I flipped it upside down, wouldn't it look exactly like that one?
Yeah.
Tell you what, folks, I'm kind of previewing some information here, but that negative, all that negative does at the beginning of your function will take a graph and it's called a reflection. It will reflect it. It's like looking in the mirror. If you treat this like your mirror, these are reflections of each other. Nod your head if you're okay with that. So that's what the negative will do. It says, oh, you have this function going this way? Nice. If I put a negative in front of it, it's just going to flip it. They even both touch the origin, don't they? Origin, origin, just flipped over. That's what that negative will do. We'll talk a little bit more about that in the next section. Shall we keep going? Kind of interesting, right? No longer just straight lines. Weird. Let's do the same idea, only now we're going to do this with this function. What are those silly vertical lines doing up there? What do those mean?
Absolute value.
Absolutely.
Absolutely. Yeah, that's exactly what it means. It means absolute value. And we're going to see how this graph looks doing the exact same thing we did over here. Oops. Make this an f of x. You know what? I'm even going to pick the same point. So let's pick 2, 1, 0, -1, -2. We always want the 0 because we want to find out what's happening on the y-axis. We need positives and negatives to figure out what's happening on each side of the y-axis. Do you remember how absolute value works?
So it's gonna be positive.
no matter what?
Yeah.
Okay. So in our case up here, we say, take our 2, plug it into absolute value. You say, what's the absolute value of 2? And you tell me, yeah, because what it's doing is finding the distance from 0. It's just counting over unit by unit. So 2 is, well, equal to 2. Absolute value of 2 is 2. We get our point 2, 2. If I plug in 1, how much am I going to get?
1.
Good. 1, 1. This is pretty nice so far. How about 0? 0, 0. Negative 1. Now wait a second. Negative 1. If I plug in negative 1, notice how what I'm talking about up here, I'll do this one written out. What this says is I have the absolute value of negative 1 because negative 1 was the value being plugged into our x. What's the absolute value of negative 1?
1.
Yes. So this is negative 1, comma 1. Next one's going to be the same idea. You plug in negative 2 to our absolute value. What's the absolute value of negative 2?
2.
I only have a few people on that one. Are you with me or no? You sure? Okay, good. So we have some points. Let's plot these and see what this graph actually does. I want you to notice also on labeling your axes, you can label them either x, y, or you can label them x, comma, what I did over here, f of x. That's fine. Y and f of x are interchangeable. They just mean the output for your respective function. So let's plot some points. We know 2, 2 is up here. We know 1, 1 is right here. 0, 0 is here. The other side, negative 1, 1, well that's negative 1, 1, and negative 2, 2. That's weird. We get a similar shape as this. However, I want you to notice something on this, all right? Pay close attention. There's a difference. This is not a parabola up here. Watch. We had 0, 0, we have 1, 1, we had 2, 2. Would we get 3, 3?
Yeah.
And 4, 4, 5, 5, 6, 6? We'd get negative 3, 3, negative 4, 4, negative 5, 5, right? That is a straight line on each side, but watch what happens. Here, yeah, you got a straight line. Over here on this side, that's a straight line. Our graph is kind of like a V. It's just it's a V going up at 45 degree angle, a V. Why? What does absolute value do? What's absolute value do?
The distance.
What now?
It's the true value of the number away from 0.
Okay, it's the value of the number away from 0. That's great. It's how many steps away from 0 it is. So if I give you a positive, does it change the positive? No. If I give you a negative, what's it do? So imagine this. If I just give you f of x equals x, that would be this line. Check it out. You don't have to draw this, just watch. This would be a perfectly diagonal line. This would be f of x equals x, right? Plug in the number, you get out whatever you plug in. What absolute value does, it says, oh, everywhere you had a negative, I now kick it up and make it positive. So it takes this line, this half of it, that's on the negative side of our x-axis, and it flips it up there. It's reflecting just that part of it. That's why you get that V out of that thing. Raise your hand if you understood that. That's why we get the V. So where we normally would have a negative, now we get a positive out of it. That's the only thing. Let's see what this plus 1 does. So stick with me on this. What's the absolute value that says plug in 2 and then add 1 to it? What's the absolute value of 2?
2.
And then plus 1.
3.
So we get a point 2, comma 3. How about the next one? Let's plug in 1 together. Absolute value of 1, everybody.
1.
Plus 1?
2.
Good. 1, comma 2. How about 0? Let's plug in 0. Absolute value of 0?
0.
Plus 1?
1.
So 0, comma 1. We're not at the origin anymore. Well, let's try negative 1. What's the absolute value of negative 1?
1.
And then plus 1.
2.
Oh, we get 2 again. Weird. And then negative 2. Absolute value of negative 2 is plus 1?
3.
Let's see what happens. I'm going to say x, and since we're using g of x, I can call this axis g of x as well. Can I tell you what graph we're working with in this case? So let's do this. Let's plot some points. We have 2, 3, that's here. We have 1, 2. We know how to plot points. We'll just do that. We've got 0, 1. That's not the origin. That's up here. Then we have -1, 2. We have -2, 3. Do we get a similar looking shape? And it's still a V. But what happened? I want you to look what happened. Here we knew that this negative, all that negative did in front of the function is take the original function and flip it upside down. True? What does this do?
Move that.
Shifts it where? Up 1.
One.
Why do you think it shifted it up 1?
Plus one.
Because of the plus one.
If it had been -2, where would this have shifted?
Down.
You're understanding the idea of a vertical shift. This right here, this +1, it says every time you plug in a number, you're going to do the original thing, right? And then you're going to add 1 to it. You're adding 1 to the height of your function is what you're doing. If it's outside of your function, like this says absolute value, and then you get the +1 afterwards, it says you're doing whatever you're doing originally, and then you're tacking 1 onto it. It's tacking 1 onto the height every single time. So whereas we got the origin, we're getting 1 higher. Whereas we got a level of 1, we're now getting level of 2. Level of 2, now we're getting level of 3. It's just adding 1 onto that. If it had been -2, it would have been subtracting 2 off the level. So this, at the end of our function, that +1, or a -2, or a +5, or whatever, what have you, that is a vertical shift. It's going to either move it up or down, depending on whether it's positive or negative, respectively. That's what this is doing. How many people feel okay with that? Okay. Now, the question is, what would have happened if I would have had this inside the absolute value? Would it have still been an up-down shift? And the answer is no. No, it's not. We'll look at that in the next example. By the way, I need you to memorize these graph shapes. Know that an x squared will always give you a parabola. Know that an absolute value is always going to give you a v. It's always going to give you a v. Know that our linear graphs, we can always graph those. Know that those make straight lines. And memorize the next one I'm going to give you here. No, I just used +1. Let's make it +2, so you don't get those examples confused. Again, we're going to make a table. Again, we'll use 0. I'm going to use 1 extra point so you really see what's going on. Now let's try some points here. Is 1 a good point to plug in? Can you find the square root of 1?
No.
You can't?
Oh, one.
Okay. How about the square root of 2? If I plugged in 2, would that be okay?
No.
You could find it on your calculator. It'd be 1.41 blah 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 forever, never, never, never. Is that something you want to try to grab?
No.
No, so let's be a little bit smarter than the problem here and pick some numbers that we can plug in reasonably. So I know I can plug in 0 because the square root of 0 is, that's easy. Square root of 1 is 1. Give me another one that's easy. Let's plug in 4. Give me another one past 4, which is easy. 9. Yeah, 9 would be a good one. Let's also try some negatives. How about -1 or -4? So in this one, we're going to be using 6 points, okay? We're going to try. I'll deal with this one in just a second. We'll do this one first. So when we plug these in, we're going to take 9. We'll plug it into the square root of x. That'll be the square root of 9. What's the square root of 9?
3.
So our point is 9, 3. Okay. Let's try 4. Let's plug in 4. What's the square root of 4? I'm going to get 4, 2. 1 we just talked about. We'll plug 1 into our function. We'll get the square root of 1 is 1. So we get 1, 1. 0, the square root of 0 is okay. You can have the square root of 0. It just says, what number times itself will give you 0? What number is that? 0. Yeah, sure. 0, 0. Now, -1. Here's what this says. The value of our x in this case would be -1. So the negative would go with that x value. So this would be square root of -1 with a negative inside the square root. Can you do that?
No.
No, no.
How about this one? -4 would be square root of -4. Can you do that? Can you do it with any negative? So the question is, if I can't do this with any negative, am I going to have anything on the left-hand side of my graph?
No.
I can't plug in any one of these numbers. I'm not going to have anything over here. My graph is just going to be a one-sided graph, just these points on the right-hand side. This is undefined. We can't do that. Also, don't mistakenly reverse these points, okay? We're not going 1, 2, 3 on the x-axis anymore. We're going 1, 4, 9. So when we plot these, I'm going to go in reverse order. We have 0, 0. That's here. Sure, I have 1, 1. That's here. This is why we use more than 2 points, because right now that looks like a straight line, right? Look what happens next, though. I'm not going to 2 anything. I'm going where?
1.
All the way over to 4 and then up to 2. So 1, 2, 3, 4, 2. That's about there. And next thing, to get to 3, I got to go all the way over to 9. All the way over to 9. Ladies and gentlemen, nod your head if you understand where those points are coming from. Okay. Next up, am I going to have any point over here?
No.
I can't even plug in a negative. This is going to be completely one-sided graph. It's just going this way. So on this one, I go, oh, all right. I'm going to draw a nice smooth curve, starting at origin, and it keeps on going. It's actually flattens out a little bit more than that. In fact, if you look at this, what this actually is, value for value, is similar to a shape we just had. What was that shape at the beginning part of the class? It's like half of a parabola on its side. Took the parabola and went just like that, you'd get that shape and cut off half of it. You can't have the bottom half, otherwise it's not a function. But this top half right here, that's very similar to a parabola. You with me on this? Now the next one, we got to go kind of quick. We only have like a minute or so.
Does that have a name?
Yeah, it's a square root function.
I mean, that line? You know, like you have the parabola.
No, they're actually, I mean, it's named after, the parabola's the only one that we really have a name at this point. We're going to have hyperbolas later on. But this one, I mean, it's not called the V, right? That's the name. We call it a V because it looks like a V. But that's the absolute value function, and this is the square root function. We could name it Tyrannosaurus. I don't know where that came from. The next one, in our last minute here, I am also going to pick some points that are good for us on this case. That's going to allow us to find square roots after we do the inside addition. So 0 is going to work. In our case, I want you to notice something, please. If I have -1, it's going to be okay in this case. Do you see why? I take -1 plus 2, well, that's 1. -2 is okay. That's fine. -2 plus 2 is 0, right? Yes. Square root of 0 is 0. We can do that. -3 would not be okay. So I'm going to pick these 3 points and then maybe 1. I'm sorry, 2. Because 2 plus 2 is going to give you 4. So let's try this out. If I take 2, I get the square root of 2 plus 2. That's giving me the square root of 4, 2 itself. 0 would give me No, I probably don't want to pick 0. I will probably want to pick something like 1. No, I don't want to pick 1 either, do I? Maybe stick with these 3 points. I just want you to see what happens here. -1 plus 2, that's going to give you +1. That's going to give you 1. If I do -2, square root of -2 plus 2 is 0. Square root of 0 is 0. If I plot these points, 2, 2, -1, 1, -2, 0. -2, 0 is here. -1, 1's here. And then 2, 2 is over here. Do you see that I get the same shape of graph? Same shape of graph, right? Same exact shape. What happened?
They moved.
It shifted it, which way? Shifted it 2 spots to the left. Do you see? This is interesting. Most people make a mistake right here. I know I'm going over by like 30 seconds or so, but, oh, a minute. So most people make a mistake and go, oh, plus should be a shift to the right. That's how we want to do it, right? But that plus right here, within the function, it says this. You plug in a number, it speeds up what's going on, like a timeline. It says, if it happened here, now it's happening sooner. Sooner on a timeline is this way. Does that make sense to you? This graph is now happening sooner. You're adding 2 to it. That's why it's shifting it left, not right. That's kind of the key point there. How many people understood today? Good.